Section 3.2, the International System of Units. We're going to study about the 5 base units that we use in chemistry, and then also metric units that we would commonly use for things like length, volume, mass, temperature, and energy. Know those concepts. Those are going to be the key things that will be questions on the test, so make sure that you understand those when we get done with this section. In science, we've got to have some type of standard that we're going to use, and for us, the metric system is the standard that you use in science, and that was established back in 1795 back in France. It's kind of evolved now. We now call it the International System of Units, commonly abbreviated SI. And this is just simply a revised metric system. It's mostly the same thing. There's a few minor things. That was adopted in 1960. So for a long time, you had the metric system for, a couple hundred years. Now, 1960, we've decided we're going to update a little bit. We've got the SI system. There are 7 base units that you use in the SI system. Everything else is a derived unit. In other words, you get it from taking one of those or multiple of those base units and multiplying or dividing them together. In other words, if we talk about length, the SI unit would be the meter, and if we want to talk about area, there's no SI unit for area, but it's derived from length times width, so it's meters. If meters is our length, square meters would be our area. Our typical ones that we use for chemistry are going to be meter, kilogram, Kelvin, second, and mole. And most of those you're probably familiar with. Kelvin is temperature. We're more familiar with maybe Celsius, but Kelvin is going to be the SI term, and mole is probably the new one. Mole is simply a number. It's a really big number, but it's a number. Just like dozen stands for the number 12, mole stands for the number 6.02 times 10 to the 23rd. So like I said, a really, really big number in that case. So here's our SI base units. Once again, the base unit and the symbol, what they stand for. We talked about the 5. There are 2 other ones, the luminous intensity one, candelas, and electric current amperes, which we would use maybe in physics, but we probably won't use much in chemistry. If we want to talk about prefixes, the metric prefixes, these are the most common ones, I guess, that we will use. We're kind of getting more and more familiar with ones like mega. We kind of see those a lot with computers, mega and giga now and kilo. Most of these other ones you've probably seen. The ones that you really need to be familiar with would be kilo, centa, milli. Those are kind of ones that I think you just need to have as standard things. You need to memorize those or remember them. The other ones, I would probably give you that if you needed to know. You say, hey, what's micro mean, or nano, or pico? Those maybe are not as common. But when we talk about really, really small things like atoms, we're going to talk about, things. So like the size of an atom is often measured in picometers. All right, so let's talk about length. SI unit for length is the meter. Should be familiar with that already. Metric units, common ones, centimeter, meter, kilometer. Those would be some pretty common things that you would measure things in. For volume, remember volume is space occupied, the amount of space that you take up. We usually think of it as length times width times height. If our SI unit for length is a meter, the SI unit for volume becomes cubic meter. Now cubic meter is a pretty big amount. If you think of a meter by a meter by a meter, that's pretty large, and most of the things that we're measuring in science are not going to be near that big. So we do use kind of a non-standard term quite a bit, and this you're probably familiar with liter, but technically it's not an SI term, but a liter is 10 centimeters by 10 centimeters by 10 centimeters. So if you look at a ruler and you find 10 centimeters on there and do a cube like that, you would end up with 1,000 cubic centimeters, which is 1 liter. Okay, so this makes it interesting. If you think about this, we've got 1 liter, which we said equals 1,000 cubic centimeters. Also, 1 liter is going to equal 1,000 milliliters, because milli means 1,000. Therefore, these two terms, milliliter and cubic centimeter, are equal. So 1 cubic centimeter is the same thing as 1 milliliter. So they're interchangeable. So when you're measuring something, like if you're in a lab and you're measuring something in a graduated cylinder, and it says measure 5 milliliters or 5 cubic centimeters, those are both the same thing. Either one of those, you should be able to figure that out. Just go, go to the 5 milliliter mark or whatever. Okay. So typically we're going to use things like liter, milliliter, cubic centimeter, which is the same thing. Microliter, we won't measure anything that small, but it's not uncommon in chemistry. And one thing to keep in mind, that whenever we use something that measures volume, it is always calibrated to a temperature, because the volume changes based on the temperature of a substance. So a lot of times they would be calibrated to 20 degrees, because that's pretty common room temperature. 20 degrees Celsius is about 68 degrees Fahrenheit. So they would be calibrated to a certain temperature. The difference isn't going to be a lot, so most of the things that we do is not going to make much difference. But if you want to be real exact, when they're doing stuff in lab, they might need that, and there's the difference. All right, let's talk about mass. And when we talk about mass, we've got a standard kilogram mass. And if you go to France, there is a place where they've got this mass like this sitting under this glass jar with a vacuum. It's sealed, and it is exactly 1 kilogram. That is our standard measurement for mass. And if you change that, it's all based on that particular weight right there. So I always wanted to get in and cut a little bit off, and then it would mess up everything around the whole world, because everything's compared to that. But probably be hard to do. I imagine it's probably locked up pretty tight. I wouldn't be able to get there. Originally, they got a kilogram from saying, hey, let's take mass of 1 liter of water at 4 degrees. 4 degrees is where water is the most dense. So they said, take 1 liter of water at 4 degrees, whatever the mass of that is considered to be 1 kilogram. So that was where it originally came from. They did go to the standard later, but they're all going to give you they should give you all the same amount. Typically, kilograms, grams, milligrams, micrograms. Once again, we're not going to be measuring probably on that smaller side. Be aware that when we're talking about mass, we really need a platform balance. In other words, you need to balance the two things to measure mass. Mass and weight are different. Weight is actually the force of gravity on an object, the pull of that, and that can change. So if I measured something here, found out what the weight of it was, and it would actually change if I went to the top of a mountain. It would change slightly. If I went down deep in a valley, closer to the center of the earth, the gravitational pull is a little stronger. It's going to change. If I go to the moon, it's going to change. But the mass on all of those places would all be the same. So I could take my 2-pan balance, and the two things would always stay the same. So that's the difference. Mass is really the amount of matter, how much stuff there is in it. It is not the pull of weight. If we talk about temperature, we're simply talking about how hot or how cold an object is. And be aware of this, that heat always moves from hot objects to cold objects. It's not the other way around. So if I put two things together, like a hot piece of metal and an ice cube, and a lot of people would think, oh, the ice cube is cooling off the hot metal, but technically the hot metal is giving its heat to the ice cube, so the hot metal is actually raising the temperature of the ice cube. That's actually what happens. Now, of course, in the process, the temperature goes down of the hot object. But if you followed the flow of heat, it's always from hot objects to cold objects. For most things, as you heat them, they tend to expand. This is why I said with volume, we want to make sure that we have a temperature. We need to be aware of it because things do expand typically with temperature. One exception, one major exception, is water. Water is one of those few things that as you get it colder, when it changes from water to ice, it actually expands, and that's unusual. We'll use either the Celsius or Kelvin scale. All our thermometers are Celsius, but it's pretty easy to convert to the Kelvin scale. On the Celsius scale, freezing is 0, boiling is 100. We will not ever use Fahrenheit scale, and we won't probably convert between those two. Kelvin scale, that freezing point is 230 or 273.15, boiling 373.15. And notice that they do not write a degree sign. There's no degree sign for Kelvin. I guess I didn't write it for the Celsius, but you would. But for Kelvin, they don't. So you would just simply say 273 K, and that indicates Kelvin temperature. Notice that the difference between freezing and boiling on both of these is 100 degrees. The increments are the same. It's just where they start that's different. So the degrees, each of them are the same. 1 degree Celsius, 1 degree Kelvin, it's the same. But Kelvin starts at absolute 0. Absolute 0 is the coldest temperature you can get to. To convert between the two, it's pretty simple. To go from Celsius to Kelvin, you're just going to add 273. To go from Kelvin to Celsius, you're going to subtract 273. I always just think of this. Alphabetically, K comes after C, so K is bigger than C, and our difference is always 273. So I just think of it, my K answer always has to be bigger than Celsius. The difference is 273. That way I can just say, well, if I'm going from Celsius to Kelvin, I'm going to have to add 273. If I'm going the other way, I'm going to subtract 273. Not usually too difficult to make conversions between these two things. So let's just take a look, real simple, at this first example. It says normal human body temperature is 37 degrees Celsius. What is the temperature in Kelvin? Well, 37 plus 273, 310 K. So normally right now you guys are probably running around at 310 K for a temperature. All right, why don't you do these two? Pretty simple. Write those out. What I'd like you to do is actually stop the videotape, and then when you're done, start it up again, and I'll tell you the answers in just a little bit. So take and stop it. Go ahead and do it. All right, so 77.2 K, if we're going to change that to Celsius, minus 273. If we do that, we get negative 195.8. That'd be our Celsius temperature. Now, if we use 273 and I didn't put any decimal after it, my least common place is the ones place, so I need to round off to the nearest one. So actually it'd be negative 196 C. Okay, for 17, you're going to do the same kind of thing. So the melting point, you're going to take 960.8 and you're going to add 273. You're going to end up with 1,234. And for the boiling point, 2,485. Units of energy. When we're talking about energy, what we mean is the capacity to do work or to produce heat. And we're going to talk about it in terms of either joules or calories. Those are pretty common units, although the SI term is the joule, so that's the one we'll use the most. A calorie, originally it was defined as being the amount of heat needed to raise the temperature of 1 gram of water 1 degree Celsius. So 1 gram or 1 milliliter, if I want to raise it from 10 to 11 degrees, that would be 1 calorie. That's a little c calorie. That's not like the big food calories like we think of. It's 1,000th of that amount. So a joule is not, is even smaller than a calorie. It's 0.239 calories, or 1 calorie is 4.184 joules.